The basis of present-day weather forecasting is the weather map. In short, it is the main instrument of the forecaster. The construction of the weather map depends on the collection of weather reports from a large number of reporting stations covering a wide area. At each fully equipped reporting station, the following elements are observed at fixed times, called the synoptic hours. Temperature. The temperature of the air is given by the dry bulb thermometer. From the temperature of the wet bulb, the humidity can be derived. The maximum thermometer gives the maximum temperature reached during the day. It must be reset after each observation. Similarly, the minimum thermometer gives the minimum temperature reached during the night. This thermometer also requires resetting after the reading is taken. Weather at the time of observation is also observed. A note is kept of weather since the previous time of observation. The type, amount, and height of cloud are also observed. Only the height of cloud below 10,000 feet is recorded. Visibility is observed by noting the furthest visible of certain selected objects. The rain which has fallen since the previous time of observation is measured in a graduated glass measure. The wind direction and force may be read off from the record of a Dines anemometer. Pressure is observed on a Q-pattern barometer and reduced to sea level. The tendency. The tendency is the form and amount of pressure change for 3 hours prior to the time of observation, and is obtained from the barograph and from the difference in the readings of the barometer. The large amount of information obtained is reported in coded form for brevity and economy. These 5 simple groups of figures give detailed information concerning 16 elements observed at one station. But the forecaster's knowledge of present weather must cover a wide area if he is to be fully informed. A large number of observing stations is therefore necessary. Ships at sea help to complete the network of observing stations. Speedy communication of reports from the reporting stations to the forecaster is essential, and all modern means are used to secure it. By radio and teleprinter, reports are received by the headquarters of the forecasting service. Weather, however, is not confined within national frontiers, and for this reason it is necessary for countries to interchange weather reports. Collective issues of weather reports are therefore broadcast by wireless by the meteorological headquarters of each nation. By international agreement, reports from France, the British Isles, Iceland, Holland, Belgium, Switzerland, Italy, French North Africa, Spain, Portugal, the Azores, and Madeira are broadcast by Paris. Reports from Germany, Greenland, Denmark, Norway, Sweden, Estonia, Latvia, Lithuania, Poland, Slovakia, Romania, Hungary, Bulgaria, and Iceland are broadcast by Berlin. Reports from Italy, Yugoslavia, Albania, Turkey, Iraq, Greece, Syria, Cyprus, Transjordan, Palestine, Egypt, Malta, and Libya are broadcast by Rome. Reports from the very large number of stations within the Soviet Union are broadcast by Moscow. London is responsible for the intercontinental transmission of European reports to America. This is made in exchange for a similar transmission from Washington. Meteorological information is thus made the common property of all countries, so that all may construct similar widespread weather maps. A weather map is constructed by plotting around each reporting station the different observations made at that station. By the system employed and the use of symbols, the large amount of information reported to the forecaster can be plotted in small compass over each station. The figures of any particular element are easily picked out because of their position relative to the station. For example, because of their position, the forecaster knows that these figures refer to pressure. Examination of the collective barometer readings reveals that over South Scotland and North England, pressure is below 990 millibars, the initial 9 being understood. In other areas, it is higher than this. Between the region where pressure is below 990 millibars and that where it is above 990 millibars, there must be places where pressure is exactly 990 millibars. The position of the isobar of 990 millibars is obtained by interpolation. Isobars for other pressures are similarly obtained. It may happen that the isobars form closed curves round an area of low pressure. Such an area is called a depression, or low. The next most important element to the forecaster is temperature. Temperature is shown to the top left of the station circle. It is plotted in degrees Fahrenheit. An examination of the temperature distribution reveals that to the north of the line shown, the air is relatively cold, while to the south, the air is relatively warm. The figures specifying dew point are shown in red at the bottom left of the station circle. Dew point is also plotted in degrees Fahrenheit. A comparison of dew point readings reveals that to the north, the dew point is relatively low and the air comparatively dry, while to the south, the dew point figures are higher where the air is relatively moist. Wind direction is shown by an arrow flying with the wind. Wind force is indicated by the number of barbs. It will be seen that there is a marked difference in wind direction between the relatively cool, dry air and the moist, warm air to the south of the line. It is obvious, therefore, that the line shown is a boundary between air masses not only with different temperatures, but with different general characteristics. Air which has remained for some time in polar latitudes will have acquired the low temperature and low humidity characteristic of these latitudes. It is called polar air. Polar air may arrive over England following a very direct path. Such an air mass will have its characteristics only slightly modified. Polar air traversing a large expanse of ocean is heated by contact with the sea and is further modified by picking up moisture. Such an air mass is classified as maritime polar air. Polar air which travels over the extensive land mass of the continent remains dry. It is very cold in winter, but may be heated considerably in summer. Such an air mass is classified as continental polar air. Air which has remained for some time in tropical latitudes will have acquired the high temperature and high humidity characteristic of these latitudes. It is called tropical air. Tropical air may originate over an area far to the westward of the area shown. Tropical air in the course of its movement into temperate latitudes over the ocean is cooled, and its relative humidity is increased. Such an air mass is classified as maritime tropical air. Tropical air reaching temperate latitudes after traversing the continent is cooled, and in winter it will have lost some of its moisture in rainfall on the way. In summer, it may be very hot and dry. Such an air mass is classified as continental tropical air. Air mass analysis is of fundamental importance in modern forecasting. Very often, the distinctive characteristics of polar and tropical air are retained, and the transition from one air mass to another may be relatively sharp. So sharp, indeed, that it may be represented on the weather map by a line. The difference in the direction of movement of the two air masses may be merely relative. Such a line is called a front. The front at the surface is the boundary between these two air masses. But this boundary extends into the upper air and may be considered as a sloping surface, the cold air lying under the warm air in the form of a wedge. Depressions frequently develop at a front. A wave-shaped distortion of the front occurs. This is associated with a local fall of pressure, and a depression develops in consequence. Continuous deepening and development of the depression then takes place over the area shown. Circulating winds develop around the depression, further distorting the shape of the front. The section of the front in advance of the depression where warm air is overtaking cold air is called the warm front, the international symbol for which is shown. The section of the front where cold air is overtaking warm air is called the cold front. The international symbol for the cold front distinguishes it from the warm front. The direction of movement of the front is indicated by having its appropriate distinguishing marks placed on the side of the front towards which the front is moving. The warm air between the two fronts is called the warm sector of the depression. The depression has a velocity roughly equal in speed and direction to that of the air in the warm sector. The air in the warm sector moves at a greater speed than the warm front itself. Accordingly, it overrides the relatively cold and dense air in advance of the warm front. In vertical section, the warm air may be represented as rising over the cold air as though it were ascending a slope. The slope averages about 1 in 100 and is here shown greatly exaggerated. As the warm air rises over the cold, it expands and cools. Condensation in the form of cloud takes place, the type of cloud depending on the height at which it forms. At a height of 5 miles, Cirrus cloud appears. This would normally be observed at 500 miles in advance of the surface warm front. Reports of this type of cloud may be one of the first signs of an approaching warm front. Nearer the surface warm front, high altostratus and then nimbostratus will be found. These would confirm the earlier evidence of the approach of a warm front. The importance of a wide distribution of reporting stations will now be apparent, for the approach of a warm front, heralded by reports of cirrus, from Stornoway, Wick, Aberdeen, and Yarmouth is confirmed by the nimbostratus reports from Blacksod Point and Falmouth. As the surface front is approached, the clouds thicken, and the height of their base becomes progressively lower. Rain reaches the ground some 200 miles in advance of the front, and from here onwards it may be continuous until the front is reached. The series of events associated with the advance of the warm front are illustrated by reference to a typical selection of surface reports. First, the temperature. This is comparatively low in the cold air in advance of the warm front. At the warm front, the temperature is found to be appreciably higher. The dew point. The dew point is also found to rise abruptly at the warm front. The small difference between the temperature and the dew point at the warm front is an indication of the high humidity of the air in the advancing warm sector. Cloud. Cirrus cloud was reported 500 miles in advance of the warm front. The cloud amount was reported as a trace. Nearer the warm front, the cloud type was reported as altostratus and nimbostratus, with skies completely overcast. Note the report of rain at this station within the last hour. Note, too, the increase of wind force as the warm front is approached, and the change of wind direction at the warm front itself. But a similar series of events will be experienced at any one station in the path of the advancing front. In the warm sector, weather may be fair. Sometimes, though, drizzle and fog are experienced. A station within the warm sector would then report overcast skies, drizzle, and poor visibility. The area of the warm sector is gradually reduced by the ascent of the warm air at the warm front and also at the cold front. At the cold front, the dense cold air undercuts the warm air of the warm sector, forcing it to ascend. Here again, the ascent of the moist warm air produces cloud. The slope of the surface of discontinuity between the two air masses is of the order of 1 in 50. As this slope is much steeper than that of the warm front, the ascensional movement of the warm air is more violent than in the case of the warm front. Precipitation is heavier and lasts for a shorter time. The cold, dense air in the rear of the cold front pushes forward, and its arrival is frequently marked by a pronounced squall. Sometimes the advance of the front is retarded near the surface by friction. The cold air at some height above the surface then advances more quickly than that at the surface. The breakdown of this extremely unstable state is associated with a squall of unusual intensity. In the warm sector near the cold front, the vertical temperature distribution is frequently favorable to the development of large-scale instability. Large cumulonimbus clouds will then develop for several miles on either side of the front. Heavy rain may occur, perhaps accompanied by thunderstorms. The cold front on any particular occasion may have any or all of the features just described. When isobars are drawn, they will be found to turn sharply at well-marked fronts. This implies that at the passage of a front there will be a sharp change in the behavior of the barometer. The importance of the observation of barometric tendency will now be apparent. In advance of the warm front, the tendency will be falling, while in the rear of it, the tendency will be falling and then steady, or falling less rapidly. The tendencies in the rear of the cold front show a marked rise in pressure. Rising pressure is associated with descending air. So, in the rear of the cold front, clear skies are common. The number of vertical strokes in the station circle indicate the amount of cloud reported. It will be seen that in the cold air there is very little cloud at some stations. This station reports cumulus cloud and local showers. Cumulus cloud and local showers are particularly liable to develop in polar air. As the cold front advances and the area of the warm sector gradually diminishes, the cold front ultimately overtakes the warm front. The single composite front formed by the coalescence of the cold and warm fronts is called an occlusion and is represented by the appropriate international symbol. The occluding process involves the encirclement of the depression by cold air and the lifting of the warm sector above the surface. When this has occurred, the depression is said to be occluded. The occlusion first begins to appear near the center of the depression and continues progressively outwards until the entire warm sector has been lifted above the surface. The cold air mass in advance of the occlusion has had a different life history from the cold air mass at the rear of the occlusion, so that there may be a marked contrast between them. The air behind the occlusion may be colder than that in front. In this case, rain falls on both sides of the occlusion at the surface. The rainfall at an occlusion occurs partly on account of the continued ascent of the warm air and partly on account of the interaction between the two cold air masses. If the air behind the occlusion is warmer than that in front, rain falls only in advance of the surface occlusion. After its occlusion, the depression ceases to deepen and eventually becomes a stationary or slowly moving system of circulating polar air, giving but little rain. This is the final stage in the life of a normal frontal depression. Nevertheless, small discontinuities may develop in the primary circulation of depressions of this type. Disturbances may then develop at these discontinuities, and rotate round the primary depression in a counterclockwise sense. Such disturbances are called secondaries. They frequently become intense with strong winds and heavy rain, and the primary then becomes relatively unimportant. Occasionally, the disturbances cause the isobars to assume a V-shaped form. This is called a trough of low pressure. It will be remembered that the depression just considered originated to the southwestward of Ireland. Commonly, the cold front in the rear of the occluded depression will be found to have progressed further southwards. The conditions at such a front are still favorable to the development of depressions. When a new depression commences to form, it will be further south than its predecessor. A series of depressions may form along the front in this way. The cold air thus tends to reach lower and lower latitudes behind each successive depression until finally, behind the last depression of the series, it sweeps southward and goes to feed the trade winds of low latitudes, so breaking the continuity of the front. Since the dense cold air is associated with rising pressure over a wide area, an anticyclone may develop. An anticyclone is an area of high pressure enclosed by isobars. The wind blows in a clockwise sense round the anticyclone, but with a slight component outwards from the center of high pressure. The outward flow of air implies that there must be a source of supply aloft, and that air is flowing downward or subsiding to maintain the flow. The subsiding air is warmed by the compression experienced in the course of its descent. Although the subsidence may occur at the low rate of only 300 feet per day, the warming effect is such that fine dry weather is commonly experienced in summer. In the upper air, the warming effect is frequently so much greater than that near the surface that an inversion develops. Over the sea, layer cloud may then form under this inversion. Such cloud can be very extensive and persistent in winter. Over the land in winter, the clear skies associated with an anticyclone permit the earth to radiate its heat at night. The air near the ground is then cooled to below its dew point. Anticyclones are generally even more extensive than depressions, and anticyclonic weather is quiet and settled. Their speed and persistence depend on the temperature of the upper air. The outward extension of an anticyclone is called a ridge or wedge of high pressure. The movement of a ridge of high pressure is controlled by the movement of the areas of relatively low pressure on either side of it. The weather in a ridge is commonly fine, like that of the anticyclone of which it forms a part. The extent of a ridge is generally not great, so that the fine weather associated with it is not persistent. Where the ridge of high pressure is common to two anticyclones, so that there are in juxtaposition two anticyclones and two depressions, the region between them is called a cull. A cull is a region of indefinite winds, and almost any weather may be experienced in it, depending on the history of the air masses flowing into it and their interaction. Air mass analysis, involving the study of the physical properties of the air, is a highly specialized branch of the forecaster's work. Pilots should take advantage of the opportunity provided at their local meteorological stations to consult the forecasting expert and to discuss the weather map with him. This should always be done before undertaking cross-country flights or considering air operations over a long period.